Good afternoon, everyone. And yeah, this is in this presentation, we are going to discuss about imbalanced data set. This is the first and also the last paper. We are going to discuss about the imbalanced data set. In this particular work, we are going to discuss on a loss function that helps us to learn from imbalanced data sets. This work is done by Kairikau, Colin, Adrian, Nikos, and Tengyu. And this group of researchers are from Stanford AI group and at Toyota R&D. And let's get right into the presentation. Okay. So I put this presentation in a few different blocks so that we can easily digest it. Motivation, introduction, related works, proposed solution, and experiments and results, then conclusion, then comments and takeaway. Let's get into the motivation. The motivation for this work is to understand why the imbalanced data sets are affecting the deep learning algorithms performance. We have other algorithms, say SMART. It's used for classical machine learning algorithm, but it's not so much helpful when it comes to deep learning algorithms. And now that we know the data imbalancing is an issue, let's learn a little more about what is data imbalance and so on. First, why do we care about imbalanced data sets? Primarily, often these data sets follow a long tail distribution. For example, the iNaturalist data set from 2018, it's a natural large-scale species classification data set over 8,000 categories. If you look at its distribution, that's the number of samples for training and validation set. In validation, it's fine. Like for every class, we have equal number of samples. But however, when we go to the training set, it's not the same case. And to mention that the y-axis in this graph is actually log scale. So now that you can understand the magnitude of disparity we see between the number of examples for each class. Moving on. So now that we know the data imbalancing issue, why don't we just get equal number of samples for training and testing distribution? It turns out it's not always easy to get such a data set. For example, let's take self-driving. Like we wouldn't be getting a data set for equal number of samples for accident case and also for normal case. Same goes for medical imaging. It has many issues, like we couldn't be having a disease like cancer patients imaging, cancer CT scan, and also normal CT scan. We would have a more normal CT scans than we compare to the abnormal, like a cancer CT scans. And there is also privacy issues that also hinders us from getting a more balanced data set. These are two sources that we get data and how it's affected. And we go to images. One such example is NUS wide data set. It has more than 5,000 user provided tags and close to 250,000 images. However, if we take the ground truth, there is 81 classes. Within those 81 classes, there are a varying number of samples, as we see in the histogram above. There are some samples with, as we see, like few hundred examples, and there are some samples with, say, more than 8,000 and 7,000, 80,000 samples. So there is a huge disparity between the minority and majority classes. This is the image data set. And if we take one example for a video data set, that one is AVA. That's a video data set for post and person-to-person interaction data set. The examples are shown on the left side. And if we look at the samples, the number of samples, and when we take the pose for swimming class, we have like 141, and crawling it's 161. However, if you look at the standing, it's more than 200,000 samples. That's a huge variation within the classes. So these are some examples of the data sets that we use in our deep learning algorithms having imbalancing issue. So what is actually the issue with these data sets? Let's learn about it. The issue is when we fit a model on these data sets and then look at the training and testing error for the minority classes, it's usually bad. And one such example from this work is, let's take an CIFAR data set. It's not imbalanced data set. We artificially imbalance them like a step imbalancing. So equal, the minority class will have same number of samples and majority class will have same number of samples. but there will be a disparity. The step imbalance ratio will be there. And if we take this data set and then train a ResNet32, we would arrive at this training and testing error. As we see, the frequent classes are, in frequent classes, we have a clear low valuation error and a training error, but it's not the same case with minority and minority training error and testing error. This is the problem that we are dealing with the minority, with the imbalanced classes. Now that we understood the imbalanced data and its problem, let's get some information about the existing solutions in the related works. One way to solve this problem is to do resampling. So with the resampling, first step we can do undersampling. There we have extract same number of samples from the majority class as it is in the minority class. And this way we would be ignoring lots of information from the majority class. And the situation, so that would affect our performance. The situation gets bad when the imbalance is very extreme. As we see on the right side, it's a plot between with respect to the area under the curve, with respect to the imbalance ratio for CIFAR10 data set trained on ResNet32. The performance gets poor as we increase the imbalance ratio, as we see here on the right. And other way to do resampling is oversampling. There we would oversample more from the minority class. It's comparatively a little better. However, it still has this overfitting issue, as we see on the left. And also, one way to solve this would be to have a stronger minority data augmentation so that it would capture the minority data distribution better. And the augmented data won't be the copy of the existing data rather than having a new data from the same distribution. That would help. That's one solution. And to put together the resampling as a whole, like we can do ERM. ERM is called empirical risk minimization, in which we would give equal probability for each example in a mini batch. Or otherwise, we can take equal probability for each category. That's one way of resampling. In both cases, we would be sampling minority classes often. And that way, we would be able to reduce the training error, as we see here. The training error for the minority class, the testing error, minority classes, but however, the testing error is not improved much. But the training and the validation error for the majority classes are low. That's one drawback here. And that's about resampling. And let's think the other way. The other way is to reweighting. So what is reweighting? Reweighting is like balancing the loss based on the samples that we have in each class. There are two types in it. One is to reweight based on the actual number of classes, actual number of samples in each class. That often performs poorly, that we see on the that we see here. And the other way is to do find a effective number. So say we have samples for a binary class 60 and 40. If you do inverse class frequency like we do here, you give the inverse of 60 and then do the reweighting there. And that often again performs poorly. So we need to find an effective number and then do reweighting. So that helps solve the problem a little bit. However, this way of doing is highly unstable, and optimization is difficult. And moreover, that effective number is also on hyperparameter. We need to do multiple iterations just to find a effective data set, effective number with which we can learn the data first. So that's our overhead. This is about reweighting. There are a few other methods that we can use to learn from the imbalanced data set. Some are here. One is margin loss. So there we are trying to reduce the intra-class variation within a class, and then also maximize the interclass variation. I am highlighted here because this is some work this particular paper tries to build on. And other idea is to do label shift and domain adaptation. It's simply, we don't usually get to know the training and testing distribution of the imbalanced data set, but however, sometimes we do. In those cases, we can do reweighting or resampling to improve the performance. And finally, we have the meta-learning. Meta-learning, as we've seen before in this particular presentation series, When we have a fewer number of samples to learn from, we can use few-shot modeling to learn from them, particularly the tail distribution that we seen earlier. It's easy to model them. However, it's computationally expensive. So given this, the authors, after thinking through all this existing solution, they think they can come up with a new approach that could benefit everyone. So what is it? So they want to improve performance on the minority classes. And how are they proposed to do that? They want to have a stronger regularization on the minority classes. That's something we mentioned earlier while discussing the related works for the word sampling. So let's take an example. As we see on the left, there are frequent classes, and then there are minority classes. And we want to, what the authors mean by stronger regularization is this. They want to have a stronger and a very complex model to be put on the majority class, and a very lenient model and simpler model put on the minority class, so that the minority classes will have a little wiggle room to move, to allow some misclassification and still perform better in general. That's the overall idea for this particular work. And moving on, now that we know we are going to work on the margin-based regularization, let's recap over the margin-based data-dependent regularizer. First, what is a margin? So when we say when you have a sample in a class, when we say it's a margin of a sample, it's usually the distance, the distance between the prediction of that particular sample with respect to the decision boundary. That's with binary. What if we have multi-class? When we have multi-class classification, for example, in that case, the margin would be the distance between the prediction of that particular sample and the second largest logit in that particular class. So that's how we define the margin. Now that we know margin, we can now define margin for a training class for a J. So in that case, we look at all the samples, margin of all the samples in a particular class, find the minimum of it. That's the margin for that particular class with respect to other classes for classification. Now that we know the margin and training margin, now we can define what's classical bound. For the classical generalization bound, it's usually defined as imbalanced test error. It's usually less than or almost equivalent to the inverse of minimum margin times the root square of number of samples times the root square of a proper complex function, complexity measure for the hypothesis class that we are dealing with. In this case, we would arrive at equal length margin for the majority and the minority classes. As we see on the right. For the majority is on the left side and minority is on the right side. Each will have a equal margin with respect to the decision boundary. But that's with the data dependent usual well-balanced class. However, we are not dealing with a well-balanced data set. So we need to make it balanced. So how are we going to do that? So we are creating a balance setting of the earlier form. So then we will arrive at this particular form, and we want to minimize the right-hand side by means of constraint optimization. So what is the constraint that we do here? We put a constraint that the boundary of, when summed together, the boundary of margin 1 and margin 2, the class 1 and class 2, should be equivalent to a constant. So with that constraint, we are minimizing the right-hand side. It's a constraint optimization. We do it analytically to get the optimal solution. The optimal solution is the boundary with which we can actually give a tighter boundary for the majority class, like we see here, and then a very large boundary for the minority class, as we see on the right. And this is with the optimal solution. The optimal solution in which the boundary would be inversely proportional to the fourth root of number of samples. And as usual, the standard case would be the gamma 1 and gamma 2, both boundaries would be equal. So that is the math behind this particular idea to increase the to put a strong regularization for the minority class, thereby increasing its boundary. Now that we know what to do, we want to enforce this particular boundary. How are we going to do that? So we are going to encourage the distance or buffer between the largest and second largest logit for each class. So that way we would arrive at uh, margin infused cross entropy loss of this following form. This the authors call it label distribution aware margin loss, or simply LDAM. That is a main contribution from this work. And the authors didn't stop right there. They want to learn a little bit more from the previous works. They are the empirical risk minimization, ERM, resampling, and reweighting. They all have their own drawbacks, like was training error, heavy overfitting, and difficulty in optimization. One example is, as we see mentioned before, optimization. The green bars are the reweighting method. They perform even bad for the majority classes and leave alone minority classes. So that's some drawback with the reweighting. So the authors want to learn from this. So they introduce a new method, improved upon the existing ones, called deferred reweighting. So what is it? It's a deferred reweighting. It could also be resampling. It means applying the reweighting and resampling after annealing the learning rate. That means after some certain epoch points. So as we see on this particular graph, for the graph between the error and the epoch, the deferred reweighting performs better. To explain, the CB is class balanced, RS is resampling, and RW is reweighting. And the dotted lines mean the training, and the solid line mean the testing. And we see overall reweighting performs a little bit better than the existing ones. So the authors wants to capitalize on this particular work. They don't have a well-bound theoretical proof for this, as they have it for the label distribution aware margin loss that we discussed just now. However, this works, uh, it improves the performance in practical cases that the authors mention it explicitly. That's about the two main approach, one side approach they propose to handle this data balancing issue, imbalancing issue. Now that we know the proposed solution, let's get right into the experiments. And in experiments, the authors use two data sets, three data sets. One is CIFAR10, CIFAR100, and then iNaturalist. iNaturalist is naturally available imbalanced data set. However, the CIFAR one is not. So the authors want to artificially imbalance it, but they cannot imbalance this randomly. So they follow a certain procedure. They introduce the imbalance ratio. That it is actually the ratio between the number of samples in the frequent class, the majority class, divided by the number of samples in the less frequent or minority class. And they introduced imbalancing. They tried two methods. One is long-tailed imbalance. So that they have an exponential decay in sample sizes across different sizes. So they won't have same number of samples in each class. They would have a decaying level of samples. And the other one is step imbalance that we've seen before in the related works. That we have minority classes will have same number of samples as do the majority classes. And one thing they notice is it helps to distinguish the minority class and majority class, so that we could see how good our method performs with the two types of imbalance ratio. Now that we clear on imbalance ratio for the balanced data sets like CIFAR, let's get into evaluating a imbalanced CIFAR data set. So there we have the same CIFAR10 and CIFAR100 data set applying imbalanced data types, long tail 10 step with ratio of 10 and 100. We apply it on the existing methods like ERM, focal, and then class balanced reweighting, class balanced resampling, and class balanced focal loss, and also the new methods like LDAM, and then hinge loss with deferred resampling, and LDAM with hinge loss and deferred resampling, then margin loss with the deferred reweighting, then LDAM with the default reweighting. As we see, the LDAM with the default reweighting performs better with CIFAR 10 and CIFAR 100 dataset. Moving on, when we look at the visualization of the training and testing error or validation error with the CIFAR 10 dataset, we see the validation, training and validation error for the majority classes still remain the same. However, we are able to drastically reduce the training error and somehow reduce the validation error. So that's an improvement. Moving on, we then experiment on iNaturalist dataset. We again have the state-of-the-art methods, URM, and class balanced focal loss. Then we also mix and match with the proposed method LDAM and deferred reweighting, ERM, and then deferred and stochastic gradient descent. There as well we see improvement overall, and the top one means it's all the numbers mentioned here are the error percentage. Top one error means they are calculating the error with respect to the first highest logist, and then so there it's prone to error because it's a hit or miss situation. However, when you go for top 5, they are expecting to have the correct result with the top 5 logits. If it is there, then it improves the result, and it will have a little wiggle room for error. So that's why we see less error in top 5 compared to top 1% error. That's on the evaluation. And so now we finished the evaluation on the data sets using this proposed approach. Let's summarize what we have seen before so far. So we discussed what is data imbalance and how it occurs, then how it affects the deep learning algorithms performance. Then we explored the solutions, existing solutions, and their drawbacks detailing. Later, we discussed the solution proposed in this work, namely the label distribution over margin loss and deferred reweighting. Then we applied this approach to the standard data sets, and then so it discussed its results. And that's the conclusion of this particular presentation. And the paper and code is available, the code are available, and it's applied for classification. I believe it could be applied for other tasks as well. Thank you.